one more thing that's important to know, that it's important to establish before we move on to fields, is that there's a relationship between the least upper bound and the greatest lower bound. Okay? To state that relationship, suppose that S is an ordered set with the least upper bound property. Okay, so what are we saying here? This is already starting to get interesting because we're saying that suppose S is an ordered set with the least upper bound property. So that means already we're not talking about rationals. We have to talk about some other set that does have this property. We haven't even constructed such a set yet. At this point, we don't even know whether it's possible. We've defined a property here. We don't even know if there's a set that will, if such a set even exists. That's what we're going to have to construct. But so we're already looking at, this is partly why one of the things that's so cool about abstract math, we're defining a relationship, and we're just assuming, it's like, let's think about what this means and what can we conclude from this. So we're now going to talk about the relationship between the least upper bound and the greatest lower bound in a set that has the least upper bound property, without ever having established that such a set even exists or not. But if it exists, then this is going to be true. So it has the least upper bound property, and then we have a subset of S called B. B is not empty. It's always the same given, same criteria. Is not empty. And B is bounded below. Okay? So what does that mean? S has the least upper bound property, so it's something more than rational numbers. B is a subset of S. B is not empty, and B is bounded below. That means that B is here somewhere, and that there is a least, that it's bounded from below. So it's not infinite to the left. It's not like everything, all numbers less than 5. It has to be, there's some point at which nothing else is in B. So then, we're not done with the definition yet. Let L be the set of all lower bounds of B. Then, so here's the relationship. Then, alpha equals sup L exists and alpha equals the infimum of B. And in particular, infimum B exists in S. So what are we saying here? And why is this not necessarily obvious? Okay, so we have this set B. It's bounded below. And we want, so that's what we're looking at. We have a set that's bounded below. We don't know anything else about it, but it definitely is bounded. So we want L, we're now making a new set, L, to be the set of all the lower bounds of B. Okay, so if B stops here, then everything to the left of that is going to be a lower bound of B. So L is the set of all of those lower bounds. Then the supremum of L exists. So what that means is that if you have a set of all of the lower bounds of B, that set is going to have a supremum. And it's the same number as the infimum of B. The important point of this theory, the other important point of this theorem, is that we've only defined the least upper bound property. We didn't actually say anything about the greatest lower bound. What this says is that if it has the least upper bound, then there's also going to be a greatest lower bound. And again, we've actually looked at all these examples before with the previous videos again. So if we had A over here and B over here, and say R less than 0, R greater than 0, this is basically the same situation that we're talking about. So here's the lower bounds of A, or the lower bounds of B are everything in A. The upper bounds of A are everything in B, okay? So just say it one more time. What we want to prove is that the set of all lower bounds of B has a supremum, and that that supremum is the same as the infimum of B. So the least upper bound of L is the greatest lower bound of B. That's what we want to prove. Okay, let me draw this one more time. So we have a set here with B. And we said that B is bounded below. So there's some boundary here. So the first thing to prove is that since B is bounded below, and L is the set of all boundaries, then we know that L is not empty. Always with these proofs, it's super easy to skip details. So we defined L, but if we're going to prove that it has a supremum, we need to start with the fact that it's not empty, because if it's empty, then it won't, in which case this whole thing won't be true. So we have to actually establish that there's always going to be one. It's obvious, but we still need to state that. So since it's bounded below, L is not empty. Let me just write that down. Since B is bounded below, L is not empty. And since L, remember, so this is L. Since L consists of exactly those elements of S which have which have y less than x. So it's exactly those elements y of S which are less than x for every x in B. Okay, so for every element of x, or for every element of B, everything less than that is by definition an L, because if y is less than every element of B, then it has to be a lower bound of B, which means it's an L. So for every y that satisfies that it's less than x for every b in x, or for every x in B, then we see that every x, every element of B is an upper bound So what did we just say? L consists of everything, of all the elements of S that are less than every element of B. That's just another way of saying that it's a lower bound. If there's a number that's less than everything in B, it's a lower bound of B, right? L is all of those numbers. Everything, every number that's less than everything in B. So we see that if that's the case, then the opposite is true too. That means that if L is all of the y's that are less than everything in B, then what we're saying is that everything in B is an upper bound of L, right? Because everything here is greater than everything here. So all of these are an upper bound. So we just established that if this is all the lower bounds of B, this is all the upper bounds of L. So just to state the obvious once again, therefore, L is bounded from above, namely by everything in B. Now, we started by saying that S in this, the statement of this theorem has the least upper bound property. The least upper bound property says that if a set is bounded from above, it has a least upper bound. So given that that S has the least upper bound property, since L is bounded from above, L has a supermem, which we will call alpha. Call it alpha. Okay? So same thing as before. We established that L is bounded from above. The fact that we're stating that S has the least upper bound property, that means that L must have a supermem. So again, we're just saying that alpha equals the supermem of L. Now, so now we're going to try to connect it to B. So let me draw the picture again. So we have B's are over here, L's are over here. We have that this is the least upper bound of L. We're calling that alpha. And now we want to see how we can connect alpha to the set B, okay? So if we have a gamma that's less than alpha, then gamma is not an upper bound just make all the letters look the same, and then you can't tell me that what I'm saying is wrong. Is an upper bound of L. So if there's a gamma that's less than alpha, we've established that alpha is the least upper bound. So if there's any number that's less than alpha, then it cannot be an upper bound of L because we said that alpha is the least. So if it's not an upper bound of L, then gamma is not an element of B because we've already established that every element of B is an upper bound of L, okay? So if gamma is not an upper bound of L, then gamma cannot be in B. So if it's over here, then now we've said that it can't be in B. So it follows from this that alpha is less than or equal to x for every x in B. Okay? So what we're saying is basically the opposite of this cannot be true. It can't be that we have x less than alpha, because we just established that if something is less than alpha, then it's not in B. Okay? So this cannot be true. If it's not less than, it has to be greater than or equal to. So it follows that alpha has to be less than all of the x's. Okay? It can't be that x is over here, because then x wouldn't be in B. So alpha must be less than all of them. So we just established that alpha is less than everything in B. That means that alpha is a lower bound of B, therefore alpha is in L, right? We just established that alpha is smaller than everything in B. That means it's a lower bound of B. So that means it's in L, because L is the set of all lower bounds of B. So what we've shown here we've shown that alpha is an element of L, but that beta is not an element of L if beta is greater than gamma. It can't be an L because alpha is the supermum, right? So you can't have it bigger. This is the biggest. This is nothing in L is bigger than this. So if beta is over here, it can't be an L. So what we've shown here is that alpha is a lower bound of B, but beta is not if beta is greater than alpha, because it's not an L, and L is all the lower bounds. So alpha is a lower bound of B, but anything bigger than alpha is not a lower bound. Okay? So say that again. What does that mean? Alpha is a lower bound of B, but anything bigger than alpha is not a lower bound of B. There are no lower bounds of B bigger than alpha. What does that mean? That means that, therefore, alpha equals infimum B. Which was to be proved. Quod erit demonstrandum. So what did we show? The theorem was that if S is an ordered set, that has the least upper bound property, and we have a subset of S that's not empty and it's bounded from below, and that L is the set of all of those boundaries, then L has is bounded. It has a least upper bound, and that the least upper bound of L is the same as the greatest lower bound of B, and that in particular, if there's a least upper bound property, there's a greatest lower bound property. And so that's what we have shown. That's what we've shown here, that the least upper bound of L is the greatest lower bound of B.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. and click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.